Okay, in this video, what I want to do is describe the relationship between a balanced chemical equation and the amount of energy that can either be released or absorbed by that particular chemical reaction. Okay, so technically speaking, we're looking at a thermal chemical equation. This happens to be the reaction between propane and oxygen. This reaction is a classic combustion reaction, which means that the propane is actually going to burn. So, if you've ever looked at a cigarette lighter, oftentimes the fluid fuel that they're using for that is a mixture of propane and or butane, and in a lot of homes across the United States, propane is actually used as the gas that is utilized in cooking and so on. Now, this balanced combustion reaction is coupled to this value over here to the right in blue, and this is called the enthalpy of the reaction, and this is delta H naught. So this is the amount of heat energy in this case that was released, or that is released, when this particular reaction is carried out at the thermodynamic standard state, all right, which is at 25 degrees centigrade and 1 atmosphere of external pressure. That's what the naught means right here. All right, and I made the comment that energy is released in this reaction. We can tell that that happens because of the negative sign that's in front of the numerical value here, the negative sign that appears in front of the 2045. And then the units are in kilojoules per, now this is the key thing right here, per mole of reaction, per mole of reaction. And what that means is that if we carry out this reaction where we combine exactly the amounts of propane and oxygen dictated by the balanced equation, so 1 mole of propane combined with 5 moles of oxygen, and the reaction goes to completion, so all the propane and all of the reaction all of the oxygen reacts in a 1:5 ratio, then this much energy is going to be released. Now, what does it mean that the energy is going to be released? All right, so if we were to carry this reaction out in a calorimeter, all right, so we have a coffee cup, it's got some water in it, we have a thermometer, and we were to carry out this chemical reaction between the propane and the oxygen, we would see a temperature increase occur in the calorimeter. All right, so energy would move from the reaction into the calorimeter, and as a consequence there would be a change in temperature that would be positive. All right, so if you think about this, it should make sense to you, because propane is a gas that runs gas stoves, all right, and when you turn on the stove, the gas comes out of the fixture and there is a blue flame. So the point is that this is a reaction that produces energy, all right, energy is released, and that energy is what we use to cook food and so on. So this is what we call an exothermic reaction. It is exothermic. Exothermic, because energy is released by the reaction, indicated by the negative sign in front of the numeral or the numerical value. All right, now what we want to do is explore how to use this number to figure out the amount of energy released for any amount of input of propane. So let's say that we want to burn 2 grams of propane, and we're going to assume that we have an excess of oxygen. So we might be burning this propane in air, for example. All right, and what I want to do is figure out, all right, how much energy is going to be released when we burn 2 grams? Because this number right here, this is telling us how much energy is released when the balanced equation operates, which means that is the amount of energy released when we burn exactly 1 mole of propane, and 2 grams is not 1 mole. So let's see what happens here. So we have 2 grams of propane. All right, and what we're going to need is the moles. So we're going to divide by the molar mass of propane, which is 44.094 grams. All right, and where this number comes from is we're just taking 3 times the atomic mass of carbon, which is roughly 12, and then adding that to the molar mass of hydrogen, which is compensated for 8 hydrogens. So when we divide the 2 grams of propane by its molar mass, what we get is 0.04536 moles of the propane. Now, since this value is per mole of reaction, and since propane has a coefficient of 1, this enthalpy value, this delta H value, is already in terms of the propane. So to figure out how much energy is going to be released when we burn 2 grams, we simply take the moles that we just calculated for the propane and we multiply it directly by the amount of energy, which is per mole of chemical reaction, or per mole of balanced equation. And since the coefficient is 1, this is already in units of propane. And what we get is minus 92.76 kilojoules of energy released. So this is the amount of energy that would be released if we burned only 2 grams, which is a fraction of a mole. All right, it's approximately 4.5% of a mole of propane, and so we produce proportionately an amount of energy that will be or that will correlate to the input of this much propane. Now the question becomes, what about the oxygen? All right, and how does this relate to this number? All right, and so what I want to do is take a moment to look at that. All right, so if we take and we determine the number of moles of oxygen required to react with the propane. All right, so what I'm going to do is take the moles of the propane, and then we're going to solve for the moles of oxygen that reacts with the propane. So we're using the mole ratio of oxygen to propane. And what we find is that if we burn 2 grams of propane, we're going to need 0.2268 moles of O2 to react with that. So we're going to need 22 roughly, or about 23% of a mole of oxygen to react with all the propane here. All right. Now the question becomes, how do we figure out how much energy is going to be released by this? And we're going to utilize the same relationship that we did for the propane, which is this number here. However, what you need to recognize is that the delta H naught per mole of reaction is based on the balanced equation. So in other words, this number, minus 2,045 kilojoules, is per mole of each of the components of this reaction based on their stoichiometry, based on the ratio in which they appear in the balanced equation. So for oxygen, the amount of energy released is going to be minus 2,045 kilojoules per 5 moles of O2. Per 5 O2s. All right? And this is going to equal a minus 409 kilojoules energy released per mole of O2. Now, since we know the moles of O2, we can multiply that value by now the moles of energy that we have in proportion to the per mole value of the O2. All right, and what we're going to get is minus 92.76 kilojoules. So the point here is to recognize that the energy that was stipulated way up here at the top, that is being produced based on the balanced equation, is the energy that is being released per mole of balanced equation, and the values that we're getting when we look at the individual components should be the same, and it is.